Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss the topic control memory. So, control memory in control unit. So, control memory is the memory which is present in the control unit, that is called control memory. So, in previous class, we have discussed about the control units. So, we can implement the control units in two ways. One is the hardware control unit and another one is a microprogrammed control unit. So, in this lecture, we are going to see the control memory in control unit. So, in general, the control unit, it can be used to generate some timing and control signals. So, see here. So, control memory. So, if you consider a basic digital computer system, mainly it consists of three functional parts. So, that are CPU. So, first one is the CPU, Central Processing Unit CPU, and memory, and the third one is the IO devices, input or output devices. So here you can see the basic digital computer system architecture. So here it consists of a CPU, memory, and along with some input devices and output devices. So these are the three main functional parts. Okay. So if you consider a central processing unit CPU, again it consists of three parts, that are control unit, ALU, arithmetic and logic unit, and the third one is some registers. Okay. So inside some registers are available. So these are the three important components or parts of the CPU. First one is a control unit, second one arithmetic and logic unit, and third one is the registers. So already we know about the ALU. So ALU means arithmetic and logic unit. So it performs several arithmetic and logical operations. So arithmetic operations are addition, subtraction, multiplication, and division. And coming to the logical operations are and, or, XOR, not, complement. So these are all the logic operations. So finally, this ALU, it performs various arithmetic and logical operations. Okay, so in order to perform these arithmetic and logic operations, it requires some registers. So the CPU, it is having the registers too. Okay, so registers are nothing but a group of flip-flops. Using that, we can store some information. Okay, so these are the different parts of the CPU. So here, the control unit. So control unit is there. So the control unit, it can be used to generate a sequence of micro operations. So using this control unit, we can generate some micro operations. So micro operation. So what is micro operation? Micro operations are the operations we are performing on the data storing registers that are called micro operation. So so micro operations are nothing but the simple operations like movement of data from one place to the another place, modifying a value present in registers, performing arithmetic and logic functions or operations, and overriding a value in a register. So these are all some simple micro operations. Okay. So that micro operations we can generate by using the control unit. And also the main function of the control unit is to generate some timing and control signals. Okay, timing and control signals, because the digital computer system, it is a collection of various modules. Okay, so in order to work all these modules properly, it requires some timing and control signals, because all the digital modules has to coordinate with each other in order to perform a dedicated task or specific task. Okay, so in order to coordinate all the digital system modules, so it requires some timing and control signals. So these timing and control signals are generated by using this control unit. So that is a main function of the control unit. So using the control unit, it will generate a sequence of micro operations, and also it generates the various timing and control signals. Okay, and the complexity of the digital system is derived from the number of sequence of micro operations that are to be performed. So the methods of implementing control unit are hardware control unit and microprogrammed control unit. So already we have seen what is the uh, uh, functioning of the control unit. So this control unit we can implement in two ways. The first one is the hardware control unit. So hardware control unit, and second one is the microprogrammed control unit. So we will see what is a hardware control unit and microprogrammed control unit. So first one is the hardware control unit. So in this hardware control unit, the timing and control signals are generated by using some hardware components. So we are generating using some hardware. So like some logic gates, encoders, decoders, multiplexers, demultiplexers, and finite state machines. So these are all the different digital circuits. Okay, that nothing but a combinational circuits. Okay, so this hardware control unit, it was implemented by using combinational logic circuits. That means so the combinational logic circuits, it includes all these. So logic gates, decoders, encoders, multiplexer, demultiplexer. Okay, all these are all. So the hardware control unit, it was implemented by using the this combinational logic circuits. So the combinational logic circuits are the output depends only on the present input. It will not depend upon the previous output. So that means the performance of the combinational logic circuits are faster because the output only depends upon the present input only. It will not depend on the previous output. Okay. So these control signals generated by using the hardware using some conventional logic design techniques. Okay. So second one is it involves fixed number of instruction. It involves the use of fixed instruction. That means we have in this hardware control unit, we have a limited number of instructions. So if you want to implement any function, then we can do it using only this fixed number of instructions. Okay. And the second one is fixed logic blocks of and or arrays. So we have a limited number, fixed number of and or arrays, and encoders, decoders, etc. So here we have a limited number. And coming to the characteristics, key characteristics. So the key characteristics of the hardware control unit are the high speed operation. So these are the hardware control unit are very high speed because they can generate different timing and control signals at a very faster rate. Because already you have seen, so these hardware control units are designed using the combinational logic circuits. That means the output only depends upon the present input only. Present output depends only on the present input. So that's why we will get the output at a faster rate than using the sequential logic circuits. So here we are not using any sequential circuits, like nothing but we are not using any memory based elements. So that's why here it is having high speed of operation and expensive because it is expensive because we require more number of combinational logic circuits, like we require more number of encoders, decoders, multiplexers, demultiplexers, and logic gates. So we require. So as the number of components are increasing, what will happen? It will become expensive and relatively complex. It is a relatively complex because suppose if you are designing any control unit, it requires more number of logic gates, more number of encoders, decoders, multiplexers, demultiplexers. So that's why it is a relatively complex. Because suppose if you want to modify any instruction, then you need to change the connections between the logic gates or encoders, decoders. So that's why relatively it is a complex and no flexibility of addressing new instructions. So here we cannot implement any. Here there is no flexibility for addressing new instructions because here we have to use only whatever the instructions are available. So we cannot implement any new instructions. So these are the key characteristics of the hardware controlled unit. And examples of the CPUs using this hardware control units are Intel 8085, Motorola 6802, Zilog Z80, and any RISC-based CPUs. So RISC means reduced instruction set computer. So next one is okay. So see here. So this is a control unit of a basic computer. So hardware control unit. Hardware. Okay. So if you look into the operation, so in general we will store the program in the memory. We will store the program in memory. So memory, it contains multiple memory locations. Okay. So every memory location, it is having some address like this. Okay. So here it will store in the memory. We will store the program. So program is nothing but a collection of instructions. Okay. So whenever any instruction fetched from the memory. Okay. So whenever the instruction is fetched from the memory, that instruction will be placed in the instruction register. Instruction register. IR, shortly we can call instruction register. Okay. So this is a instruction register format. So it is a 16-bit register. So the size of the instruction register is a 16-bit. So that means total it is having 16 bits. That means if you represented 0 to 50. So 0 to 11. So 0 to 11. So that means total 12 bits. So the 12 bits it represents the address of the operand. So address of the operand. So operand is nothing but the data on which we are performing the operation. That is a operand. Okay. Next coming to the 12th. So 12th bit, 13, 14. So total it contains 3 bits. So these 3 bits it represents the opcode. It represents opcode. Opcode means operational code. So this operational code, it specifies what type of operation the CPU has to be performed. Okay, that is a opcode. And coming to the last bit, that is a 15th bit, that is a indirect. So that can be represented with I. That can be represented with I. I means indirect bit, or we can also call the extended flip-flop. Extended flip-flop. So I. So it specifies the type of the instruction, whether that is a memory referential instruction or direct address instruction. So when I is equal to 0, that is a direct address. Direct address. So that means when I is equal to 0, the instruction is having the direct address. When I is equal to 1, then it specifies indirect. The instruction is having indirect address. Okay, so that is one. So here we have seen opcode. So opcode means operational code. So using the 12th bit, 13th bit and 14th bit, it will specify the opcode. That means what type of operation it has to perform. So that means here total 3 bits. So that means 2 power 3. So 2 power 3 is equal to 8. So that means total it can perform 8 different operations. 8 different operations. Okay. So how we can implement all those 8 operations using a decoder? So using a 3 by 8 decoder. So 3 by 8. 3 by 8 means 3 inputs are there and 8 outputs are there. So these are the inputs. 12th bit, 13, 14. That are inputs. And outputs are this 0, 1, 2, 3, 4, 5, 6, 7. So total 8. 8 outputs are there. Okay. So based on the inputs, the corresponding output will be generated. Okay. So see here. So total how many combinations? 8 combinations. So 8. So that means 8 outputs will be generated. Okay. So the input combinations are, suppose if you have a 12, 13, 14. So that are the inputs. So total 3 are there. So 2 power 3, 8 combinations. So 0, 0, 0. That is the first one. 0, 0, 1. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So total 8. So this is a 0 count. 0, 1, 2, 3, 4, 5, 6, 7. So total 8. 8 outputs. So output. Coming to the output. Outputs are okay. So outputs y0, y1. So if you represent y is the output, then y0, y1, y2, y3, 4, 5, 6, 7. Okay. So if all inputs are zeros, then only the y0 output will be logic 1 and the remaining all are logic zeros. Similarly, when the input combination is 0, 0, 1, then y1 will be logic 1 and the remaining all bits will be logic zeros. Okay. So in this way, only one output will be there. Based on the input combinations, one of the output will be high, logic high, and the remaining all are low. So like this, we can perform 8 different operations. Okay. So see. So when inputs all are zeros, then y0 will be 1. Y0. This is a y0. So y0 will be 1. And the remaining all are zeros. That means D0 control signal will be generated. D0 control signal will be generated. So suppose so see here. So let us assume when 000 is there, it performs one operation like addition. Similarly, when 001 is there, it performs subtraction. 010, it performs increment. So like the total, we can perform 8 different operations. So corresponding control signals will be generated by D0 to D7. Okay, these are the control signals. Similarly, we require timing signals. Okay, so the timing signals are generated using the sequence counter. So this is a sequence counter. So 4-bit sequence counter. So see here. So the sequence counter. So the outputs of the sequence counter are 4 bits are there. So 4 bits, 1, 2, 3, 4. So these 4 outputs we are giving to a 4 by 16 decoder. 4 by 16 decoder. So that 4 by 16 decoder, it generates 16 timing signals. 16 timing. So it is represented with T0 to T15. So total it generates 15 timing signals. So in order to perform any operation, we require this timing and control signals. So the control signals are generated using this 3 by 8 decoder, and the timing signals are generated using this 4 by 16 decoder. So this it will generate the decoder, it will generate T0 to T15. Okay, so all these timing and the control signals. So these are the timing signals. These are the control signals. So suppose if you want to perform any addition operation, if you want to perform a addition operation. So in order to perform this addition operation, it requires some timing and control signals. Timing and control signals. So suppose if the operation is add. So T0, T0, D0. So T0, D0, it represents the addition operation. That means in order to perform the addition operation, it requires T0 timing signal and D0 control signal. So all that timing and control signals we are applying to a control logic gates of the control unit. Okay. So all these control and timing signals are applying to the control logic gates. Okay. So these control logic gates will inform the CPU and memory in order to perform this addition operation. Okay. So because here we have given a timing and control signals. So using this control logic gates, this unit will inform the CPU and memory in order to perform this addition operation. So like this, it will the timing and control signals are generated. Okay. Suppose here add is there. So add A comma B. Okay. So the timing signal. So we have seen how to generate the timing signal. So timing signals. Why we require timing signal? Because when we are performing this add A comma B, it requests some timing signal. Okay. So when this addition operation is performing, the sequence counter will generate a timing signals. So timing signals means so when you are performing add A comma B, it will generate the timing signals corresponding to the register A and the register B. So during that time, it will generate the timing signals only for the register A and B in order to perform the addition operation. Okay. And coming to the sequence counter. So the sequence counter, it is having some inputs: clock, clear, increment. So increment means it will increment the count by 1 because it is a 4-bit counter, 4-bit sequence counter. So initially the count will be 0, 0, 0. After that, if you apply a clock, it will be incremented by 1, 0, 0, 1. Next 0, 0, 1, 0, 0, 0, 1, 1. Next 0, 1, 0, 0. So up to all ones. So the sequence counter, it starts counting from 0, 0, 0, 0 to it will end with 1, 1, 1, 1, 1. Okay. So from 0 to all 1, all zeros to all ones, it will count. That is incrementing. So whenever this increment signal is applied, its count value will be incremented by only 1 every time. Next, clear. So clear is it can be used to clear the sequence counter. So when we apply a clear signal to the sequence counter, it will be initialized to the 0 sequence. So starting value is all zeros. That will become a starting counter. Next clock. So because already we know, so sequence counter, it requires some clock. Okay, so this is about the hardware control unit. So the hardware control unit means the timing and control signals are generated using some hardware, like some logic gates, encoders, decoders, so all this. Coming to the second one, microprogrammed control unit. So microprogrammed control unit, the principle of microprogramming is an elegant and systematic method for controlling the micro operation sequence in a digital computer. So in previous one, we have generated this timing and control signals using some hardware. But here we are generating the timing signals and control signals with the help of microprogram. So microprogram is a collection of micro instructions. Okay. So microprogramming is a method of designing control unit in which the control signal selection and sequencing information is stored in ROM called control memory. So control memory is the memory which is present in the control unit, that is called control memory. So in the control memory, we are storing this micro program. So micro program is the collection of micro instruction. So every micro instruction, it contains one or more micro operations. Okay. So a sequence of micro instructions designed to control a specific instruction is called microprogram. So we are storing this microprogram in the control memory. So microprogram means a sequence of micro instruction. So microprogram, it is nothing but it is a collection of a sequence of micro instructions. So every micro instruction, it consists of one or more micro operations. Micro operations. Okay. So the examples of the CPUs, it is the CPU based on the microprogram control units are Intel 8080, Motorola 68000, and any CISC CPU. CISC means complex instruction set computer. Okay, so this is a microprogrammed control unit. So for each micro operation, the control unit has to generate a set of control signals. For any micro operation, any control line may be turned on or off, which represents a binary pattern. So see here, for every micro operation, control unit has to generate a set of control signals. Okay, so already we have seen. So using these 3 bits, we can generate different micro operations. Okay, so how many bits are there? 12, 13, 14. So total we have 3 bits. Okay, so the 3 bits can be used to represent the opcode. So 3, that means 2 power 3. So total 8 micro operations we can perform. 8 different micro operations. 8 micro operations we can perform. Okay, so it generates a binary sequence. That means suppose when all inputs are zeros, when all inputs are zeros, 0, 0, 0. So what is the output of the decoder? So at the zero output of the decoder will be logic 1, and the remaining all are zeros. That is the output. Okay, that means it will generate a binary pattern. For every operation, it will generate a binary pattern. Okay. So for each micro operation, the control unit will generate a set of control signals. And for any micro operation, any control line may be on or off, which can represents a binary pattern. Okay. So for next sequence, suppose if you take all ones, if you take all ones, if you take all ones, then it will generate a different pattern. So what will be the pattern generated for the inputs 1 1 1? It will generate a sequence 1 0 0 0 0 0 0 0, because when all inputs are triple one, then the seventh output of the decoder will be logic high, and the remaining all outputs are zeros. So it will be generated like this. So like this, for every micro operation, it will generate a different binary pattern. Okay. So the control word is constructed for each micro operation. A computer that employs a microprogrammed control unit will have two separate memories, that are main memory and control memory. So the programs are usually stored in main memory. So basically the programs are stored in main memory by the users. Whenever the program changes, then the data present in the memory also gets changes. Okay. So they consist of machine instructions and the data. So the control memory here, it can be considered as the ROM memory. ROM is nothing but read only memory. Read only. Okay. It is a non-volatile memory. Non-volatile means even the power fails, the content stored in the ROM will be it will be permanent. It will not get erased even the power fails. So that is a non-volatile memory. So the control memory, it can be considered as the ROM memory, read-only memory. So it consists of the micro programs that are fixed. So because it is a permanent memory, so we cannot modify. Once the manufacturer manufactured this, loaded the program into the ROM, we cannot modify. Okay, and cannot be modified frequently. Okay, so they contain micro instructions that specify the internal control signals are required to execute register micro operations. And the machine instructions generate a chain of micro instructions in the control memory. Their function is to generate the micro operations that can fetch instructions from the memory, compute the effective address, execute the operation, and return control to the fetch phase and continue the cycle. And coming to the microprogrammed control unit organization. So here it is a address sequencer. Okay. So already just before we have seen microprogrammed control unit. Okay. So in the microprogrammed control unit, we are generating the timing and control signals using some microprogram. So that microprogram, it will be stored in the control memory. So control memory. So ROM can be considered as the control memory. Control memory is nothing but the memory which is present inside the control unit. That is called control memory. Okay. So see here. So when we are storing this microprogram in the this control memory, okay. So we have a memory, control memory. So every memory location, it is identified with a unique memory address, memory location address. Okay. So here in this memory, so ROM. So in this memory, we have stored a micro program. We have stored a micro program. So micro program is nothing but it is a collection of micro instructions. So here we will store some instructions. Instruction 1, 2, 3, 4, and so on. Okay. So in the memory we will store the micro instructions. Okay. So when the CPU it execute the micro instruction at the address 4000. After executing, it has to generate the next address. It has to go to the next address. So once the instruction which is in the 4000 location is executed, after that the CPU has to go to the next address, that is nothing but 4001. So this next address is calculated using this next address generator. So this block diagram. Okay. So this next address, it is generated using this next address generator. So we can also call the address sequencer. We can also call this address sequencer. So it is a next address sequencer, a next control address register, control memory, and control data register. So these are the blocks it had. Okay. So already we have seen the control memory. So in the control memory we have a micro program. So micro program, it is a collection of micro instructions. So the first instruction is storing the address 4000. So this address, it will be stored in the control address register. Shortly we can call CAR. So currently the address of the currently executing instruction will be stored in the control address register. After that, in that 4000 location, the instruction that will be stored in the control memory. Okay. So, whatever the instruction is there in that address, that will be stored in the control data register. Okay. So the address will be stored in the control address register, and the instruction will be stored in the control data register. So let us assume first instruction is executed. So whenever the first instruction is executed, then the CPU has to go to the next address. So next address is a 4001. That means it has to, while the CPU executing the current instruction, simultaneously it has to generate the address of the next instruction. So address of the next instruction is the 4001. So that the address of the next instruction, micro instruction, is generated by using this address sequencer. So that is a operation of here address sequencer, and it is also having some control word. So control word. So the control data register, it is having some control words also, and in the control data register, along with the instruction, some other bits are there. So using that bits, we are giving to the input of the address sequencer. So with the help of the additional bits and external input, it will generate the address of the next instruction. Okay. So this is a address sequencer. So the next address must be computed once this operation is completed, and it is computed in the next address generator. So already we have seen about all these different blocks which are available in the address generator. Okay. And the main function of the microprogram sequencer are, it can increment the register by 1. Next, it can load the address from the control memory into the control address register, and it can transfer an external address or load an initial address to begin the start operation. So these are all the main functions of the microprogram sequencer. So the data register is also known as pipeline register. So already we have seen control data register. So that control data register we can also call pipeline register. So that means pipeline. That means here this register, it performs two operations parallelly. Simultaneously it will perform two operations, that are, while executing the current instruction, it also generates the address of the next instruction. It allows two operations to be performed at a time. So it allows performing the micro operation specified by the control word, and also the generation of the next micro instruction. Okay. So that's why that register, control data register, is called pipeline register, because it performs the two operations at a time. So that's why. The main advantage of using microprogrammed control unit is that the hardware configuration is established once, no further changes can be done. So that are the main drawback of the hardware control unit is, once the control unit is established, it is very difficult to modify. But we can do many changes in the microprogrammed control unit, because microprogram is nothing but it is a programming. So simply by changing the programming, then we can achieve the required functionality. However, if a different control sequence is to be implemented, a new set of micro instructions for the system must be developed. Okay, so we have seen, we have discussed both the hardware control unit and the microprogrammed control unit. So now we will see the differences between them. So the first one is the hardware control unit generates the control signals using some digital logic circuits. So already we have seen the hardware control unit, it generates the timing and control signals with the help of some logic gates, encoders, decoders, multiplexers, demultiplexers, finite state machines. So these are all the different hardware we are using. So it requires more hardware. And coming to the microprogrammed control unit, that generates the control signals with the help of micro instructions stored in control memory. So already we have seen, in the control memory we are storing a microprogram. So that microprogram consists of micro instructions. So that micro instruction will generate one or more micro operations. So micro operations are the operations that are performed on the data stored in register. Second one, the hardware control unit is faster when compared to the microprogrammed control unit. It is a faster because this hardware control unit is designed using only the combinational logic circuits. That means here we are not using any memory storage elements. So that's why the hardware control units are faster, because in this the output, present output, it will depends only on the present input only. It will not depend upon the previous output. So that's why these hardware control units are faster than the microprogrammed control unit. And it is a slower. So microprogrammed control units are slower than the other micro instructions are used for generating signals here. Third one. So difficult to modify. So these are difficult to modify as the control signals that need to be generated are hardware. So already we have seen, so for designing of this hardware control unit, we require more number of hardware. Suppose if you want to do any modification, then you need to change the connections between those hardware. Okay, so that's why it is very difficult to modify. In a microprogrammed control unit, it is very easy to modify, because it is a, so in the microprogrammed control unit, the timing and control signals are generated using the microprogram. So by changing the instructions, then we can generate the required timing and control signals. It is easy, so, but it is a difficult to modify. Next, more costlier. These are the most costlier because we require more hardware in order to implement the hardware control unit. So that's why it is a costlier. Less costlier. It is less costly because here we doesn't require any hardware. Only we are generating the timing and control signals with the help of the micro program. So that's why less costlier. Next, it cannot handle complex instructions as the circuit design for it becomes complex. So it cannot handle complex instructions because because here in the hardware control unit we have a limited number of instructions. It can handle complex instructions. It can handle complex instructions, and only limited number of instructions are used due to the hardware implementation. So here only the limited number of instructions are available. Here more number of instructions are available. And the last difference is it is used in computer that makes use of RISC, reduced instruction set computer. And here this microprogrammed control unit, it can be used in it can be used for complex instruction set computers. So it is the hardware control unit is used in RISC for RISC, and the microprogram control unit it is used for the CISC based computers. Okay, so these are the difference between the hardware control unit and the microprogrammed control unit. So in this lecture we have discussed about the control memory. So control memory and various ways to implement the control units. So here we have seen two ways to implement the control unit, that are hardware control unit and microprogrammed control unit. So we have seen each operation, and also we have discussed the difference between the hardware control unit and microprogrammed control unit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.